let me take just a few seconds for a very personal communication. We have been informed yesterday that the founder of the ManuFuture technology platform, which then generated EFRA and EIT, Professor Franco Iovane, passed away. So it's a very sad news for us, and we will try the best to continue his battle for European manufacturing. So please join me in clapping Franco. Thank you so much. Very, very quick introduction. I think that AI has been a topic which has been covered not only in this section, but is pervading also the other sections. We come from a section in sovereignty in which also we speak about AI. AI is for sure a very important technology. By the way, it's a very old technology because it has been invented in the 50s, so it's a 70 years old technology, but clearly the condition for exploit it are now, for a lot of different reasons that maybe the speakers will cover. In this moment is a technology which has a CAGR in the range of 40%, so it's clearly impressive on this point of view. In Europe, let me say we are a little bit lacking behind, but we have strong ambitions to recuperate that. I remember in Brussels that we started discussing this matter in 2017 after the famous AlphaGo win with the world champion of Go. And from that, we start a lot of discussion also with the Commission saying, well, we are lacking behind, what we have to do. For sure, AI for consumer is something which is not in the hands of European companies, but in manufacturing, in industrial technologies, I think there is still space to say something. So I leave now the floor to the first speaker, which is Sotiris. Sotiris is from the Patras universities and is working on these topics since a long time. Sotiris, the floor is yours.
Thank you so much. I'm Sotiris Makris from LMS at the University of Patras. So I'm going to talk about an old technology that we try to make it applicable to an application area that started in the Middle Ages. At least this is what we said in the previous session. Manufacturing started in the Middle Ages, so we're trying our best to find what we have to do to apply AI. So I'm going to summarize some activities that have been running around AI in Europe. And actually, this has been facilitated by the so-called AIMNet, which is a network on artificial intelligence in Europe. So the presentation will evolve around the mission, the idea, how is the situation of AI application in industry, and possibly what can be done to advance on that. So AIMNet is a network of partners combining research partners on the one side and industry partners on the other side. This network is not a running project. It is an initiative working on a voluntary basis. From our side at LMS, we had started that, and we are leading this effort, and we are very glad to keep working with these institutes and this industry. And we are trying to answer the questions that I mentioned before, and then I will try to make a bit clearer as we go. There are several things we noticed in the literature, in the several surveys. I will just bring forward one of them, which is a survey run by EIT, the Crosskick project, which has been asking what are the advantages achieved by AI so far. In this one, respondents said that maybe there are not clear advantages yet, but there is great potential for reducing costs in manufacturing and increasing the revenues in different areas in manufacturing and supply chain, as you can see in these charts. So altogether, AIMNet comes together bringing experts from different areas in AI manufacturing in Europe with different interests. And the focus is to bring the manufacturing as a user of AI, this point of view, to bring it forward. So it is a coordinated effort that aims to scale up, to promote the scale up from lab to the factory, and to help to align AI strategy and business goals together so that we can exploit how, in the end, AI can generate profit. Also sustainability and so on and so forth. It is also an initiative that we think that can help to attract and engage talent in the manufacturing world, which is a key for European industry, and it should ensure adoption and value creation. I will move on with a couple of examples, indicative examples we discussed in the network. And first, I will bring one industrial example presented by one of the leading European companies, which is Materialise. In this case, AI is used in different cases. These cases on assessing quality of 3D printed parts, and there are several challenges, as you can see, in terms of taking images, annotating defects, and processing them. There is high complexity, but there are also some other aspects like kind of skill sets needed for doing this kind of work, and also technology like visualization, for example, for assessing defects. That is an indication of the direction that has been followed by the network. And then I will move in a couple of shorter examples. This one is on material cutting and milling, and there we see a great potential on collecting data from multi-sensors in order to perform a number of analyses, like, for example, predicting tool wear, or this would affect to product quality improvement, saving energy, and also preserving natural resources, like in this case, preserving water or other cooling fluids that are needed in the cooling. There are also projects working on humans in the loop, humans in the factory, and then AI has been used here and reported by the members of the network has been used on optimizing the design of workplaces or optimizing the collaboration with robots or assessing ergonomics and so on and so forth. One example that I will try to show is this project, the Sherlock project, where different robotic systems are used in cooperation with the human. We see the use of digital technologies along with exoskeletons helping the people in the assembly process. Mobile robots used for helping people to carry big parts autonomously in the factory, a lot of AI over here. We see the case of a large payload robot which adapts its behavior to different people, different genders, different ages. So it assesses who are the people, what they're doing, and what are their needs, and it adjusts its behavior. And last but not least, I will wait for a minute. We have a case where people and robot share tasks on the same part, share time and share place, and they are actually coordinating their actions in order to achieve an efficient production of the part. Efficient means in terms of quality, in terms of ergonomy, in terms of many other KPIs. So this gives the view also of the workplace level and people and cooperation, people and robots cooperation. And then we have the level of the production line, where the aspect here is how to optimize, how to balance line. We see two examples. One is machining lines on the top, and the other one is assembly lines. And there are several challenges on how to place machinery and how to coordinate tasks and how to balance everything so that different criteria are efficiently optimized. This is one more example of what such AI system looks like. That's a tool, for example, that helps the designer of a workplace or an assembly line by proposing different design alternatives, which that would mean that it saves time and it helps to quantify the different design alternatives so that in the end the engineer can make the final decision. Different criteria are quantified, like ergonomy, for example, or the footprint on the factory, or even the energy consumed by the resources selected, the time spent, and many other criteria. So these examples, I hope they gave some idea of what AI looks at the process level, at the workplace level, and at the line level. Then there are some more things in addition to that. There is a product design vision where, again, product design is very human, intuitive, let's say, action. And there are two examples reported here on how AI can help to generate different, maybe in some cases not easy to conceive cases of designing or configuring a product. All in all, what we did is that we took the factory, we structured in 3 levels. You can see in the red level we have the process-related AI technology. At the second, the blue one, we have machine and station level for AI technology, and at the top level we have the systems level, which includes production line, supply chain, and so on and so forth. And then we identified a number of AI applications already accomplished today, maybe at a lower TRL still, and this shows that there is potential, but still a lot of work is needed. And the next thinking ahead was how to start thinking around these results and how we can maximize the impact of that. And this view shows the workflow on the top, from product design to production system planning, construction, commissioning, production, and product use. And then the different colors correspond to AI modules we have been discussing in the previous examples. And the very idea here is that, of course, each one of them can fit in different places in the life cycle. But let's assume that this is one of the snapshots. Let's assume that this is how the AI modules are used. It is possible to interconnect them, to imagine how we can interconnect them. It's not done. I don't have seen anyone trying to do that, but the idea would be to interconnect them, different modules accessing data and results from other modules, and altogether creating a bigger AI system that would eventually lead to the achievement of the different KPIs, which is a thing that needs to work on. What kind of KPIs, what kind of business or social-oriented aspects to optimize, and how exactly to measure that. We have put some of them over here, and it's a question how this can be structured to have the maximum KPI achievement. So over, it has been thought that different technologies discussed can bring some percentage improvement in different KPIs. However, having seen what AI can do, maybe we should not be talking about percentage. Maybe we should be talking about times improvement. So instead of talking about 10%, 20%, maybe we can talk about twice or 3 times improvement. That's the kind of KPIs that we think AI can bring. And that's the kind of investigation we're trying to do in this network. What kind of achievements we can expect to have. So this summarizes what has been told or what is planned to be told, to be discussed in the next steps. So the very idea is that we want with AIMNet to accelerate the way forward, to generate the roadmap for AI uptake by manufacturing industry in Europe. We have to map to see how far AI has gone in the factories, what has it done, and how it can help to how we can help to improve the situation. This initiative aims to shape the work at the pan-European level in a community effort. Of course, there are many individual, national, or company-wide programs, but we think that the pan-European leveraged effort would be required. There is a lot of discussion as well about the regulatory framework, which for sure it has to be adopted by industry, but what exactly you have to do to be able to comply to that is a question. This generates a lot of research items in order to be able to comply to that. Then this leads to the definition of specific challenges and KPIs. I talked about the KPIs before, and so we need to move to a methodology for assessing AI performance. How do we measure and how exactly we are going to quantify the improvement? Altogether, that would lead to de-risk of this technology, and this would facilitate the use of AI tools. We hope to be able to derive with concrete guidelines to the industry Of course, taking in putting the human in the loop, which we assume is the key resource in this effort, attracting talent in manufacturing. We think that for sure it's important, and AI is the technology to bring talent of different genders, different ages, and different interests in manufacturing. Altogether, that would help to differentiate Europe globally, and the network and this effort would, and in the end, support European industry to apply at the end AI in factories. This work is being collected. This is a collective effort. It's just a short, let's say, version of the overall effort. We have a white paper where we are collecting this information, specific cases, KPIs, and future work items. The maps you can see on the right are maps of different priority areas. This has been more proposed by research partners, and these areas have been proposed by the industry. I don't have too much time right now to go through that, but this whole thing is put together in a white paper, which is being produced by the network. And as I mentioned before, this is a network putting together both research and industry partners. And for that, I hope the idea and the content of work is clear. I'm very happy to have more questions. But in the limited time, I wanted to raise the issue, what we are doing, what we're trying to do. And thank you very much for being here and your attention.
Thanks a lot to Sotiris, and compliment you stay completely fit in the timing that we had. So, okay, next is Marta Caldeiras, is Head of Research and Innovation at the Instituto Superior Técnico in Porto, and has been a national representative in Brussels for Portugal. So, thanks for being here, Marta.
Thank you, Maurizio, and good afternoon. Just a correction, it's in Lisbon, not in Porto. Okay. I have 1 more minute for that. And moreover, I would like just to add that when until the end of 2020, when working in the National Innovation Agency for Portugal, I was one of the experts that followed the coordinated plan for artificial intelligence at the European level. And now I am analyzing some use cases on the automotive sector in Portugal to try to assess what are the implications of artificial intelligence after being adopted in these factories. And this work have been done under a research project called IntelliArt, Artificial Intelligence, Effects on Work and Employment in Portugal, funded by Santander and Nova University Award. And today I will be sharing with you some of my preliminary findings, and I'm happy to be engaged in this discussion. But before that, let's set the context of AI in Europe. So AI is developing very quickly and can bring many benefits, like more efficient manufacturing and better decision making. AI refers to systems that use different technologies for analyzing written language, converting spoken language into a machine-readable format, technologies identifying objects or people based on images, machine learning for data analysis, technologies for automating different workflows or assisting in decision making. And these are the technologies that were assessed in a survey, and this is data from the Eurostat. And in 2021, it was possible to assess that 8% of enterprises in the European Union used at least one of the AI technologies that I've been describing. This means that around almost 1 out of 10 companies have used AI in 2021, either one of these technologies or more than one technologies. And also, there are some economic activities that use AI a lot more than others. And this might indicate that AI is more relevant for certain activities. And we also see that large enterprises use AI more than SMEs. And this difference might be explained, for example, by the complexity of implementing AI technologies in an enterprise. For instance, because of economies of scale, of course. If enterprises have more larger economies, the benefit from AI is bigger, but also it can be from the costs of implementing AI technologies. So in 2021, we see that the ICT sector, which is with no surprise here, was the one with the highest shares of companies using AI, and also professional, scientific, and technical services. And all the other economic activities were below 10%, and this includes manufacturing at 7% of manufacturing companies used AI in 2021. And if we see what kind of technologies were used and for which purpose, we can see that overall there is not a big difference between the different technologies that are used at the European level and in the different economic activities. But when we compare large companies with SMEs, we see that large companies mainly use technologies, AI technologies that automate different workflows or assisting in decision making, and also machine learning for data. Regarding the manufacturing sector, we can see that there is no difference between the technologies that are used. Although there is one that is bigger than, has a higher share than the others, which is the technologies that allow to make automatic decisions. And also for the purposes, we see that in manufacturing, the technologies are used mainly for the production process and also for ICT security. So in Portugal, we also follow the same trend. Also, the ICT sector has the highest share of enterprises using AI, but the manufacturing sector comes in third place. And within the manufacturing sector, the automotive sector is the one with the biggest investment in AI, and where we can find real case applications. Because if we are, in this research project, we are interested in knowing what will be the implications of AI. So we went and selected some real cases applications and tried to identify the possible effects and impacts. So one of the examples, it's about an automatic quality inspection system in an OEM of the automotive sector in Portugal. And here, computational vision and predictive analysis is being used in the quality inspection, in this case particularly for the structural glue bed applications in rear gates. So this was the first activity where this system was implemented, but now it's widespread for all the quality inspection of parts, production of parts. And this allowed an increased efficiency and productivity and quality, of course, of the products in the automotive sector, but also a reduction of waste and a reduction in the process time. But this was in a large company, because but before that, sorry, but although the quality inspection system is automatic, so it identifies where the defect is, it also identifies where the machine eventual problems, it also makes the correction automatically. But still, although it can perform all the tasks by itself, there is still needs a human in the process. So humans are still in the process, either for adding some additional feature to this system, and this requires digital skills, or to correct some event that may occur in the process. Perhaps the part is not in the correct position, and so it has to correct this so the system can work. So we can see that the workers are having a qualification, so getting more specific and qualification tasks, and on the other side, they can also have a more monitoring and control roles. But as I was saying, this is in the case of a large company, because the same system in SMEs, it's not that easy to implement. Because here, this was the case of some components and parts manufacturing for the automotive sector. This didn't work because of the existing systems, but also because of the lack of skills from the workers and also from the lack of knowledge of the managers, how to deal with this new technology, how to change their work environments to deal with these technologies. There is another example when constructing 2 production lines in an OEM where new assembly lines and new robots were introduced, and this increased the production capacity from 32 to 45 units. And also, it increased the health of the workers by substituting repetitive and physical demanding tasks, and also reduction of costs associated with the health problems. So in the Tier 1 and Tier 2 companies are very dependent on the OEM demands. And so we were seeing, because in Portugal the most of the automotive sector is on components manufacturers, and so we were assessing how these were positioned themselves to be able to continue the high exports they are having in this sector. And we see that there were some also automation systems included. They were also able to do some changes internally to reply to an increase of volume production. And this was only possible because they are recruiting operators and workers with specific skills to do this. In fact, the human resources manager told us that although these automation technologies were introduced in the factory and the number of cells were reduced, they got more contracts and because of the competitiveness, and increased their contracts and their number of workers. So finally, I just wanted to show you that this other example, which is an industrial cloud system, but this one is still in pilot project. It's not widespread in the current activity of the factory. And in this case, it started in 2019, and it will end this pilot in 2025. So the main conclusions that that we have achieved so far is that AI technologies are diverse, and they, depending on the characteristics of each technology, they may improve efficiency and productivity. Different AI technologies will have different rates of adoption. So robotics, artificial vision, predictive analysis are there already and will have widespread adoption in 1 to 2 years. But cloud, plug and produce, blockchain, and artificial intelligence will take longer to be implemented because they involve infrastructure, different technologies that need to exist so AI can run on it. So it's like if we have the automatic pilot in a plane, but we need the plane and the fuel so we can fly. So we also saw that the implementation of AI technologies so far, it's not resulting in the dismissal of workers, which is a big fear. but it's resulting in changes in organization, and mostly managers don't know how to deal with this. And also, they are augmenting their capacity to perform their roles. Although there are still some technological challenges to be overcome, for the widespread adoption of these technologies, there are additional challenges that need to be solved, such as the lack of skills, the resistance of managers, costs of implementation, low level of modernization, job displacement. But it can also be boosted because of the efficiency, productivity, and competitiveness gains, and also lack of availability of human resources to do these kind of repetitive and demanding physical tasks. These are the conclusions for the automotive sector in Portugal, but I think that this can also relate to other realities. So, thank you.
Thanks a lot, Marta, for your presentation. Well, we don't want to give you the impression that AI is only used in automotive. So the next intervention is from Andrea Greichen, a group manager, industrial and digitalization, additive manufacturing, Siemens Energy AB. So it's an application in the energy field, and we will see, and probably will come again on this point, a strict relation between AI and additive manufacturing. I have explanation for that, but can be wrong, so maybe we will discuss this afterwards. Andreas, the floor is yours.
Thank you very much. As a European, a German living in Sweden now, this is a great pleasure to be here on a European conference. And I would like to speak a little bit about how we want to implement the machine learning in our gas turbine production. So first, I need to show you one slide about the industry I work in. Then I talk about a kind of Gartner hype curve that gave us inflated expectation for additive manufacturing. And then I come into the matter of artificial intelligence or machine learning. And I hope I can give you a little bit outlook into the future, how we see it. So a gas turbine, for those of you who do not work in this industry, is an expensive piece of machinery. High temperatures, brutal loads. It is important that our products work. Otherwise, you typically read about it in a newspaper. And additive manufacturing is used since 2012 in our activities. We have here a gas turbine burner, and earlier on we cut off the red marked section of the burner, threw it away, and produced a new head for that burner. But we thought, well, if we can develop an additive manufacturing technology that only prints on the damaged 24 millimeters, that would save a lot of time, energy, and waste. And you see, this here is a picture of the manufacturing process. You see a gray surface and then a laser walking around and solidifying, welding the powder to the already solidified surface under. And on the left-hand side, I hope you in the back, you see the left downwards facing picture. That is the tip of the burner repaired directly after manufacturing. When we started our activities in 2009, and maybe until 2012, we thought that we can print everything and anything. And that was true to some extent, but most of the time only once. Already the second time or the third time, trying to replicate the same manufacturing, we had problems. And so in 2015, I remember very vividly, our management called us in and said, well, okay, guys, you have to restart again because the rate of scrap that you produce is not acceptable. So imagine yourselves in a new way. And so we started with a staircase here. And this staircase is a digitalization staircase. I will talk about that in a little while. And that is maybe here in the middle of that staircase where we are right now. So I want to point out that our journey with additive manufacturing was not a simple success story. We had our valleys of tears. And we are in this middle of this digitalization staircase, and we were forced to develop the AM cockpit. So a machine learning tool that collects a large number of sensor data and visualizes it for the human operator and the engineer. So on the left-hand side, you see 8 burner fronts being produced. It is a CAD model that is overlaid into cloud of pictures. And you see the gray picture after the recoating, and then below the exposure picture. And you can ask why is it important for us to look at this recoating? It's only powder being applied onto the surface in the powder bed. But this is essential for us. We want to have a perfect gray surface after the recoating. So every kind of disturbance in the gray surface is an indicator for a not perfectly working process. And that is what we try to indicate here. We have here this blue graph. It annotates the 8,700 layers that is needed to produce the burner front, allocates a number between 0 and 1 to each layer, and by doing so draws a graph. So I want to see a low number close to 0, and the higher the number gets, the more problems we probably will have. And in this example here, you see a beautiful industrialization already having taken place. It is a value of about 0.2, so this is fine for me. But we have one section where a high elevation is. And if we overlay the serial manufacturing of 4 identical jobs, you see that 3 of those are more or less identical. But the blue one sticks out, and that's where the operator or the engineer can focus his or her attention. So when I tried to do this as a human, I failed after 50 pictures. 50 pictures I could remember, did I already see this or not? And this is a perfect example for picture recognition as a good example for machine learning or artificial intelligence. The AM cockpit is the collecting place where we not only collect the information from the metal printers. That is what our machine supplier EOS can organize, even in an isolated mode. But we put together all the different interesting pieces of information, the powder quality, the maintenance status, the calibration of the machine, material data, the scanned geometry after the printing, and all the way through the CAD files, the printer recipe file, and then also the metadata from the customer and the factory. And with all this, we can then say something about the quality of the process. So we are soon in a position where we dare to say, this process was good, we can compare it with a good master, and then hopefully we can eliminate non-destructive and destructive testing, which is very expensive. I would love to tell you here that we are already using artificial intelligence, but that would be overselling. What we can do is we have a place now where we have this powder bed deviation graph, here a different one, and we can stack a high number of sensor values and compare those. The task now is pattern finding. So if I look at this and the filter pressure and the oxygen content, maybe I want to see the argon flow and the power, the torque in the recoater. I do not see the pattern. And I want to have an AI application that helps me to identify if you have this kind of spike and this kind of deviation, you will have a pore, for instance. I invent something now. So this is where we want to go. Pattern finding with a multitude of different sensors of different nature. It is important that we already have collected a huge amount of data, and by doing that, we hope that we are now prepared for the AI phase in our future. I want to make some observations. If you have worked a relatively long time in this industry, you consider yourself maybe an expert, you come to this position and you have to realize, well, with AI I need to relearn my trade. That can be painful for people. Recruiting is, I believe that has been mentioned already, difficult because it's still a young industry, and in a place like Finspång in Sweden, where I work, we are very far away from the cappuccino bars that maybe young people want to have. We are a traditional industry village in the middle of a forest. If you do not have big data, you cannot analyze big data. And we spent the last 3-4 years collecting this data. The monitoring of the data quality is very important, because maybe you believe that you collect the data, but your machine is down or your sensor doesn't give relevant information. We've had some, well, painful instances there. And we can simply say that we would welcome collaboration over company borders. We alone, we are too slow to get these questions solved. As a little bit of an outlook, I said that this digitalization staircase, we have come halfway from a painful traditional workshop, a lot of paper, a lot of people, a lot of problems. We have connected the workshop so that data can flow from the enterprise system into the factory, into the printer. Now we feel that we are prepared for, after this learning workshop process where the AM cockpit was developed. Now we hope that we can make the next leap to the intelligent workshop, and I would like to call it remote intelligent workshop, because it doesn't matter if I sit 30 meters from a machine or 3,000 kilometers. And the final game is the autonomous workshop. That would mean a closed loop and self-healing process. I foresee that this AM cockpit will be developed to a learning platform that remembers our mistakes, remembers not only our mistakes, but maybe in the future also other people's mistakes. And we jointly learn together and make additive manufacturing available for humankind. And gas turbines would order spare parts in printers via a cloud application. So the Internet of Things would be realized by that. We believe that additive manufacturing would contribute to remote manufacturing, to robust supply chains. We have all suffered through the COVID pandemic. But for us at Siemens Energy, additive manufacturing is absolutely important for making hydrogen combustion possible. Only with the very complex geometry that we need for mixing and cooling, we can burn hydrogen. So here comes my connection: digitalization, artificial intelligence, and sustainability, and that is the critical point for Siemens Energy. Thank you very much.
Thanks a lot, Andreas. I ask you to take note of two important concepts that Andrea pointed out. One is big data. So we were discussing why in the 50s AI was not applied, because there were not big data generated at that moment. Then there are also something which is connected to the throughput of the hardware, but this is one of the key points. So the big data are food for the stomach, which is AI. So the two things are strictly connected. And then this concept of autonomous workshop, we will come back on that. Just keep in mind, and then we will discuss. Okay, well, next one is Daniel Engel, Production Artificial Intelligence Advanced Data Analytics from BASF in Germany. So now we move to another type of industry, to chemical industry. So we see how AI is pervading different type of industries. Andrea, okay, Daniel, sorry. The floor is yours. Thank you.
Thank you. Thank you. Okay, so thank you very much. I'm here to talk to you about applications in AI in the chemical industry. So it's a bit different than what we've seen in the first two talks. So we don't have any assembly lines, no robots, with human computer interaction types of applications. But still we have data, we have the need for optimization of these processes, and this is what I want to focus on. So one, key applications in our industry, and secondly, the challenges that we meet right now in scaling these technologies. But first, let me introduce a little bit my employer. So BASF is one of the largest chemical companies of the world. We have roughly 80 billion euros in sales and 110,000 employees worldwide. Almost 800 production plants scattered across many countries of the world. some of which form so-called Verbundsites, and this is one of the I would say key strengths of BASF, yeah, where we have many plants in one place that share common infrastructure, utilize also, let's say, supply chains and different services of that site, and so we have kind of like a circular economy of our own there, and that's maybe one key distinguisher. Our products are basically distributed in all manufacturing or industrial segments, so ranging from basic chemicals and materials to surface technologies, up to nutrition, health, and agriculture. So it's quite a very broad product scale that we have, and BASF has also very ambitious goals in terms of growing their market share in these segments, while also having the goal of achieving carbon neutrality in less than 30 years, so by 2050. So that creates, say, a challenge for us from a technology provider, no? And that requires, of course, to look at the manufacturing process in one complete chain, starting from input, so procurement, from our raw material suppliers up to our own processes across many different, let's say, production steps, yeah, of different operating divisions and segments, up to the endpoint to the supplier, yeah, and now even reaching after, let's say, their customers and so on, yeah. So for us, when we talk about AI in manufacturing, that means utilization of AI technologies in our operational production. Yeah? So achieving operational excellence with AI technology. And for that, I'd like to pinpoint the applications a little bit on, let's say, an evolutionary scale. Yeah, I think it was first used by Gartner, these kind of like levels, yeah, of data analytics, and I want to pinpoint the applications on these classifications. Yeah, but first let me describe what that means. So first stage would be to have a descriptive solution. That means we look at a variable, yeah, that is not directly measured. You cannot have a sensor, for example. Yeah, for example, performance degradation. Yeah, your classical KPI in manufacturing. There's no single measurement for this. Yeah, but you aggregate a number of sensors. You look into the current timestamp, yeah, or past timestamps. You apply some function to that, and then you map that to your target variable. Yeah, that is a descriptive solution. Now, if you have inputs that range into the future, and if you want to have an output that gives an insight on how that variable derives into the future, you are in a predictive setting. Yeah, that is usually achieved by having a model, yeah, with lots of data on that, and you basically you train that model how the let's say the predictive variable behaves in respect to different inputs. So there's a predictive solution. Next, sorry. Next would be to have a prescriptive solution where you can not only show how that variable progresses in the future, but you can also show how you should vary your inputs in order to meet a certain target variable. Yeah, and lately we see also so the difference is that here still you are using pre-trained model, you are using data that you know of, yeah, and that model can then learn how variation of inputs lead to variation of outputs, and then you can have your prescriptive solution. But next stage would be to utilize basically not to have a pre-trained model in application, but to have something that is able to learn in real time. So have an adaptive model, that learns from new input in real time, and then you are in a cognitive AI state. So here I want to map some of the core applications in our industry on these scales. So it starts with the application of soft sensors and condition monitoring, for example. Classical application would be performance degradation of assets, fouling of heat exchangers, for example, health KPIs for some rotating equipment. These are all descriptive. So you look at the data in the now and in the past, and you see, okay, currently we are having that kind of performance and that kind of performance degradation, maybe, and then you can infer something about your process and then making decisions upon that. Next stage would be to actually predict how that performance is gonna behave in the future. That means you also need to have inputs in the future, say, for example, how your process will vary over time. If you have a varying process conditions, you can then map the performance of these variables onto that, and then that will give you a predictive, predictive maintenance type of application. For the prescriptive case, mostly we look at quality predictive control solutions, where we look at, for example, production of some process steps, where we train models with respect to quality, process conditions, and process control conditions. And then we see how the process control can vary and leading to a different outcome with respect to yield or process quality. And finally, we see the rise of solutions that target autonomous plants, so process that is running autonomously using more advanced AI technology like reinforcement learning. So what I've said before is, and Maurizio also said this, the core mathematical foundation of these solutions that you find, well, let's say that you apply in practice, have been around for like 50, 60 years. So what's different now? Maybe data, but we still see that there are a lot of challenges to apply that at scale, in at least for our industry. And I'd like to highlight that a little bit in those 4 dimensions that for me personally are main blockers to scale models across all assets and all production plans. So one, we still have data, at least in the process industry. We have plants that are maybe 40 years old, and they have turnover cycles of maybe 10 years. So what we need is still very scalable, non-interruptive IoT solutions where you can do clamp-on measurements, multisensoric measurements to generate much more data than you used to have maybe 20 years ago that you need for core process control. If you want to use AI for monitoring and optimization, you need a lot of more data and more diverse data, and that is one issue. Another issue is, of course, also context. Not knowing or having a lot of measurements is nice, that's one thing, but production is more than just temperature, pressure, flow, and so forth. You need to also know about the processes underneath that underlie that production. So, for example, what if products change? What if product control or production control settings change? What if the maintenance cycles change? What if product specifications change over time? So much like it was mentioned in the talk before, that diverse set of data that you need for AI in order to make sense. Yeah? And that incorporation that in some kind of connected world, yeah, say digital twin as a buzzword, yeah, and that is a key challenge for us. And last but not least, we also face some challenges with respect to organization of our own processes. So that boils down to process and people. Before we looked at projects, yeah, with a defined scope and some defined budget and some, let's say, end result. And now that is evolving more and more into a continuous integration, continuous delivery kind of process. And that's also, I think, what you need in order to develop AI in our industry further. Not think in these finite boundaries, but to learn continuously about new technologies and to deliver continuously in a other process. And also people, of course. Yeah, you need. I think a couple years ago, maybe 10 years ago, there was a huge discussion whether this is a problem of IT or OT, and who should who's more suitable to deliver solutions in those areas. And now I believe you need a diverse team. You need all kinds of solutions, like your core IT guys, process control guys, automation, process modeling and technology, in order to have one incorporated team that can then scale AI in your in your production plans. That's my view, and I could go on about challenges, but time is up. Thank you very much.
Thank you, Daniel. So last intervention is from Antonio Calegari. Antonio is the CEO of Artificially, a Swiss small medium enterprise specialized in AI. So, Antonio.
Thank you very much. Hello. I realize I'm the last person between you and the beer tasting, so I'll try to be super fast and hopefully funny if I can. Well, in the previous speeches, I've heard a constant theme that I like to take on, which is the problem with talents. Sotiris said that, Andreas mentioned that the problem is to bring talents into this, and I understand Andreas' problem in bringing talents into a faraway, remote Swedish wood. But dear Andreas, don't worry, it's not a problem in Sweden or Woods. The problem of attracting real talents into industry, into companies, is extremely widespread. I just have one slide about my own company. I'm a co-founder of Artificially, together with two distinguished professors of AI. The whole idea about this company came from a big Swiss company who had a problem. The company was Swisscom, which is one of the largest, most sophisticated, rich, technologically advanced companies in Switzerland, but they hardly could hire and retain any AI talent at all. So it's not Sweden, it was in Zurich, in the center of Europe, a very brilliant and reputed company. What was the problem? The problem was that, first of all, you have very few outstanding talents in this field, because this field is very, very new. And these people are, first of all, they're nerds. So they like what they do a lot. They think it's going to change the world, and it's true. And so they don't want to waste their time and energy in a boring company. Whatever it is, any big company is boring for them. They want to be in a cappuccino shop in California, maybe, if they need to choose. The second point, a little bit more rational, is that they understand, the true talents, that this thing is moving like crazy. 40% growth year on year incredible salaries paid to talents in this field, rocket careers, if you are on top of the technology, which is changing every day, every week. So if you slip back, if you are not up to date, if you are not doing this at the top level every day, you lose your professional value. So you don't want to stay in a place where you do over and over and over the same thing, because with time, your professional value will be lost. And they know this. So they jump here and there just to make sure that their professional value and their knowledge is well kept. And this is the basic idea that came us to founding Artificially, which is, we like to call it a center of excellence. So we attract the best talents, and we give them a coffee shop environment. We are based in Lugano, which is a nice place to live, better than a Swedish food, and maybe. I would personally prefer the Swedish food, I confess. And we make them happy, and we make sure that they keep doing super top things.
They pay 15% taxes.
Sometimes not even that. We pay well, that's true. The other point is that AI needs to go into industrialization. And you also need to have people who's not only able to manage the most sophisticated applications or algorithms, but also understanding what it means to turn this into a real use case, to get it out of the laboratory, to make it work, to work with the real engineers to make things happen. So I agree, it's a big problem at the moment. It will normalize with time, but at the time being, it's a big problem, and our company is trying to give an answer to this. So just 2 words about theory. I'm not boring you about all the discussions about AI. Where is it going? Are machines really thinking? Are they individuals, or are we going to be dominated by robots? We are very pragmatical. We think about AI as the latest digital technology that you can use for your benefits, and normally they are automation and efficiency. We are not new to these kind of things. Sometimes these things happen very loudly. We call them revolutions for this reason. In the 19th century, in the 18th century, we had the official Industrial Revolution with the advent of mechanization and steam power. Then we have another revolution a century later with electricity and the assembly lines and Fordism at the beginning of the last century. Then we have a less loud and more creeping revolution in the second half of the last century with the progressive digitalization of machines and plant management systems. And then now we have Industry 4.0, which is supposed to be connected to cloud computing and IoT and all these new sophisticated things that are entering. Now, AI is as old as in 1950, but the truth is that the big technology, the new frontiers, the new things, the new technologies that are useful has been developed lately because of big data, because of computing power, but also because big data and computing power generate a lot of studies and billions and billions and billions of dollars or yuan or euros being thrown into people studying these things. So everything has happened in the last 10 years. And this has brought what I call the Industry 4.1. So it's an evolution of the automation and digitalization of industry. One thing I don't agree with some of the comments I heard before is that AI is a big investment for big companies. And I hope I will prove to you in the 3 examples that I'm showing in a second that AI can be extremely cheap, although extremely effective, even for very small companies with very little investment. You don't need to invest a huge amount of money to start benefiting from that. And this means that sometimes you leapfrog all the complex and costly things that you can find here, and you only need to have a digital machine and a little computer that can collect some data, which are not big in the way we think of them, huge data centers, but they're big in the sense that a simple computer now can collect an amount of data that was unthinkable 10 years ago. So they are big data in a little cheap PC. So we develop AI applications for tens of companies in every sector. I collected just 3 of our manufacturing examples. One is in the laser cutting, and it's a machine-assisted human interface. The other one is again in machining, but a traditional one with metal tools. And the last one is assembly. It's about glue. By the way, it seems that glue is coming over and over as a large problem. So very quickly, who of you knows how a laser machine work? Raise your hands. Who knows? Nobody. Well, that's scary. So most of the metal things that you use are done with these things. It all starts with a sheet of metal. It can be aluminum, can be steel, or whatever. It's put into this machine this way on a platform here. And then there is a laser driven by a computer that melts the metal and cuts it in shapes. This is our client, but it's one of the leaders, worldwide leaders in this kind of machines. They're engineering and building these machines. And the problem with laser machines is that you have to tune parameters according to the specific job. So if you have steel 11 millimeters with X% of carbon or whatever, you need a certain power, certain speed, certain gas pressure, and so on. And if you change something, you need to change these parameters. Otherwise, it doesn't cut well, and the quality is bad. And this job is done by a worker in every job shop everywhere in the world. Every time they have a new job, a new type of piece to be produced, or a new batch of material, which is not exactly the same as the batch before, they have to retune. This takes hours, because you have to find the right configuration of 3, 4, 5 parameters at the same time. You change one, you have to change all the others. And if you do it systematically, it takes months. So they do it like rule of thumb, and they still spend a few hours, and the result can be suboptimal. This is the reality of every job shop, of every laser machine job in the world. So what we do with using AI is a system that helps the operator getting very quickly to the optimal configuration by using a little sophisticated algorithm. It works like this. Instead of figuring out the parameters and trying them, figuring out another set and try them, it is the computer that proposes the parameters, and the operator runs these parameters. And then when they are cut, you see the cut pieces here, the operator only needs to judge by his experience which is the best one, which is the second best, which is the third best, just a ranking. There's no absolute measure of quality that can be different from client to client, and then gives the feedback to the machine. And the machine takes this information and elaborates a new set of parameters, another trial, another feedback. They normally do it between 2 and 4 times, and in the end they find the perfect one. Any question? So in this case, you see this algorithm perfectly integrated into the console of the machine. But this can also be done on a cheap computer, and if you want to try it, you can see it online. We have a demo there. Pretty simple. The video we've seen is the commercial video of the company. I'm speeding up. I'm using my time. Transfer machines are machine tools that in the same machine you have different working stations. Everything is automated so that the shape, the object can be cut from this side and then this side and then this side and then the drill and the blade and so on. And again, we use a small PC to elaborate the available data, which is the current absorption of the different tools. And by analyzing the shape of the current absorption, we could predict with very high accuracy the real life, or the real remaining life of each single tool. So the pictures are not very easy to understand, so trust me. The fact that they are straight line means that the prediction is very accurate and constant in time. And in this case, we could predict that the tool would last 1,800 cycles, 7,000, 5,000, 25,000 or more. So this allows the users of this machine to stop the machine before the tool is worn out, avoiding waste, and planning the stop of the machine so that perhaps they can change two tools at the same time. Those who use machines know that idle time is what kills the return on investment of these machines. And we could achieve a 20% reduction in idle time in extreme cases, which is a huge amount. The third example is more on normal production. Galvalux makes glasses and mirrors and assembles them into architectural products. And in the assembly phase, they have to glue things together. The bad things is that glue never comes right. Sometimes it's too much, sometimes it's too little, sometimes it's too dense, sometimes it's too liquid or the wrong shape. And we placed a very cheap commercial camera and a micro PC analyzing the images. And here on the right, you see the PC judging whether the glue is right or wrong. It's green if it's right and red if it's wrong. I've seen something similar in automotive before, systems that do quality control automatically. The big difference is that the total investment here has been probably 1,000 euros. 30 euros for the camera, well, the money they pay to us to do it properly, and 1,000 euro for the monitor that the operator is using. And this is a mid to small company doing high-end products. So no big investments. I hope I've convinced you about my three main points. And one is that talents are the scarce resource. The second is that AI is now, it's not something that will come in manufacturing tomorrow. And the third one is that it is not necessarily for big investments or big plans or complicated things. You can start step by step with little things that works, increase efficiency, and take away boring job from workers. Thank you very much.
Thanks a lot, Antonio. I think we have to keep this final statement. Industrial AI is now. It's correct. I want to be provocative. In China, the world's largest arc dam, barrier, has been completed in just 4 years. And the project leader declared that it would have not been possible without extensive use of AI. Now, the Yanggu barrier is under construction with 3D printing methods. So 3D printing is coming back again, in construction in this case, and autonomous excavators and trucks with everything controlled by AI. So we are seeing in China a model of use AI to reach autonomous manufacturing. So we saw in Andreas' presentation and also Daniel's presentation this final goal of autonomous workshop, autonomous process. So we know that the European model is not that. And we have clearly seen in the presentation of Sotiris, for example, where manufacturing, where AI is used in cobots in cooperation with humans. So we have a model which is more using AI in cooperation with humans, and in partly also the presentation of Bystronic is a sort of human-machine cooperation supported by AI. So what is the vision of the speakers? What will be the final results? Will be that AI will allow autonomous process, or will be just support to human workers? Because this will change drastically a lot of things. So I don't know who of you wants to answer, please.
Well, I believe that this AI-supported industry future comes first, and that we might wait a few years more until printers, industry machines are really fully autonomous. I would make the parallelity of autonomous driving. A level 4 Tesla is probably already for sale today, but not legally available in Europe. So I believe that, yes, there is no way of stopping it, but it will still take a number of years until we see machines fully taking over, or maybe never. But I believe that this is not so far in the future.
Okay, any other ideas?
Well, I agree with Andreas. It's a step-by-step process. So I think the ultimate goal is to reach a high level of autonomous operations. But you don't get there if you don't go through the experience of automating this little piece and that little piece, and then maybe tying them together, and seeing where you can reach full automation and where actually you cannot. Autonomous driving is a nice example. We quickly reached a very high level of automation, but we cannot really break the last 5% barrier. And this will take a lot of time, but the benefits from this 95% are huge, honestly. In the end, if you think about how a car was produced in 1920 and how it is produced now, if you look at it with the viewpoint of a person in 1920, a Volkswagen plant now, it's fully automated. You almost only see robots from that standpoint. Actually, we know we have.
That is not unmanned.
It's not completely unmanned, absolutely.
So autonomous drive will be a reality between 2030 and 2035. This is the expectation. So can we expect that also in manufacturing we will see some completely unmanned factory for the time? Who knows? So I don't think that we have to give an answer, but we leave you just with this question in mind. If there are other questions, we still have 8 minutes from 6 o'clock, and so I can open the floor. If not, I will try to stimulate also the other speakers to say something. Jose. As I said before, we know each other, but we did not agree about the question, okay? You can say.
I thought we did.
This microphone maybe.
Yeah, okay.
Okay, we have to.
Okay,
Thank you.
no microbes, no, please, thank you. So, no, a question that I was thinking of by listening to several speakers. So, somebody said we need a lot of data to have artificial intelligence because that's one of the problems we didn't have in the past. So, I think that we basically, although we can start simple things, but at the end of the day, we need a lot of data. And also, from Marta said, we need somehow some infrastructure to collect data, to process these kind of things. Now, on the other side, we have, depending on the countries, 85, 90%, 95%, 98% of SMEs in our industry, which it's a huge challenge for these small companies, as was mentioned, to have this infrastructure and then to be patient to collect these data, to make an investment. I mean, 3, 4, 5 years collecting data, and then maybe they are ready to do something on AI. So it's not easy. So my question is, well, how can we do this in these kind of companies? You addressed already. But the second question is, if you're talking about machinery, is this something that needs to be done in each company, or this is something that can be done by the machine producer as a service to the SMEs that use the machinery? So that's my tricky question.
You are touching a problem, a potential problem, which is who owns the data, okay? If you speak, I have worked 35 years as a machine manufacturer and laser manufacturers, and the position of the manufacturer is, yes, we can give you the service, but we need the data. So is like the internet providers that are giving you a lot of services free of charge, but at the end the products are you, and the data are your data, which are used by them. On the other side, some companies are jealous of the data and do not want to give. So probably the final story will be something mixed from the two. But I open the floor, Andreas.
I mean, if Europe wants to retain its competitiveness, it's probably necessary if the European Union creates a joint learning platform. In countries where one party owns everything, it is easier to command your compliance. So I believe that if Europe wants to survive in the AI race with other continents, then a European joint learning platform is mandatory. I cannot imagine any other way than the EU stepping in and taking the lead.
A final
Okay.
comment? I have it.
Please,
Thanks a
Sotirios.
lot, but I fully agree with Andreas. That is the whole point of the networking effort and coming together. Everything, people have tried individually to do things, but we need a coordinated effort all together to make a joint effort. But I wanted to add to the previous discussion, comparing to the autonomous driving or to the example of a machine builder building the machine and having the data. The key thing in manufacturing is that we shape matter, and it depends on materials, environmental conditions, people. So no one factory is the same with the other. It is going to be quite impossible. And that would be, I think that is also the challenge in AI, because AI is doing this black box input-output training that sometimes, if you do not consider the physics of the process, make it so hard. In any case, I think we all agree on the challenges. Maybe I still have open the question, are we talking about percentage improvements or times improvement? Are we going to improve 30, 40, 90%, or twice, 3 times, 10 times the process? What is the objective of improving the KPIs with AI? That's my own question, and I hope it stimulates some more thinking.
Okay, so seems that there are no questions from the audience. So we close with two minutes in advance this session. I thank you, everybody. I thank you, the speakers. I thank you, the audience. And well, see you in some years, and we will discover what the history will do. But as been said by Antonio, we don't have to fear. The dystopic vision, Terminator or so on, let's leave it at the movies. AI will be an important tool for manufacturing and will be dominated, will not dominate. Thanks to everybody, and enjoy the dinner. Bye-bye.